Welcome to class, everyone. Today we're tackling one of the absolute most stubborn bottlenecks in all of artificial intelligence. I'm talking about the synchronization problem in distributed deep learning. Think of this explainer as a bit of a technical masterclass. We're going to look exactly at how we coordinate multiple computers to train a single massive AI model without, wasting precious computational time. Let's walk through this brilliant piece of research from York University together, and we'll see exactly how they unlock a whole new level of efficiency. Here's our syllabus for today's lecture. We are going to start with Distributed Deep Learning 101, examine the synchronization dilemma, and explore the middle ground. After that, we'll break down DynamicSSP, introduce the ElasticBSP solution, and finally, wrap up by looking at the future of training. Okay, let's dive right into this with our first chapter on the basics. So I want to pose a fundamental question to you all. Since a single server might take weeks or honestly even months to train a massive neural network on a colossal dataset, how do we speed this up without the entire process just crashing and failing? Well, the obvious answer is you distribute the workload across multiple machines, right? But coordinating those machines, man, that is where the math gets incredibly tricky. To solve this, we usually rely on something called the parameter server framework. Picture it like a classroom. You have a central parameter server up at the top. Think of it as the teacher that maintains the master copy of the global model weights. Then you have your independent worker nodes down below, represented here by machines 1 through 4. These are your students. What we do is partition our massive training dataset and assign a unique subset to each student worker. So in every iteration, these independent nodes crunch the math based on their assigned data, figure out the necessary updates, which in machine learning we call gradients, and they push those updates back up to the teacher. The server then aggregates all these gradients, updates the master weights, and passes that newly updated, smarter model right back down to the nodes for the next round of learning. Now, the mathematical engine actually driving all of this is stochastic gradient descent, or SGG. Simply put, it's an iterative optimization process. The model parameters are just updated step by step using computed gradients from data mini-batches. But here is a truly beautiful critical property of machine learning that we absolutely must keep in mind today. It is incredibly fault-tolerant. These models are surprisingly robust against minor errors or a little bit of noise in those intermediate calculations. And that specific mathematical property, that's going to be the absolute key to our solutions later on. Which brings us perfectly to our second chapter, and really the core dilemma of our lecture today. How on earth do we keep all these independent student workers on the exact same page? Let's look at the two traditional extremes here. Over on the left, we've got Bulk Synchronous Parallel, or BSP. Think of this like a really strict group project, where everyone has to wait for that one dreadfully slow straggler student to finish their assignment before the rest of the group can move forward. It guarantees perfectly consistent weight updates, making it highly accurate, but it is painfully slow because your fastest machines are just sitting there spending most of their time completely idle. Now on the right, we have Asynchronous Parallel, or ASP. Here, the students just run chaotically ahead at their own blistering speed. They never wait for anyone. It's blazing fast, sure, but it is incredibly risky. Because when workers update the server asynchronously, you get what we call staled gradients. Basically, that means workers are doing complex math based on outdated versions of the model. This introduces severe noise that can literally cause the entire neural network to diverge into a totally chaotic, unusable mess. So if strict weighting is way too slow and zero weighting is way too chaotic, how do we find a workable middle ground compromise? Well, the first major attempt at a compromise was the Stale Synchronous Parallel model, or SSP. SSP basically allows workers to run independently, but only up to a fixed staleness threshold. It effectively says, okay, worker 1, you can run ahead, but if you get exactly 3 iterations ahead of our slowest worker, you hit a hard barrier and you must wait. Now, speaking as someone who really loves elegant systems, blindly tuning a fixed, static hyperparameter like this staleness threshold is just a major pain. It's rigid guesswork, and worse, it completely ignores the actual, real-time computing capacity of your cluster. And that brings us to the first major optimization in our syllabus that actively attempts to fix those rigid flaws. Now, what's really interesting about this slide is how DynamicSSP adapts at runtime. Take a look at the green, blue, orange, and yellow bars there. You'll notice each worker takes a slightly different amount of time to actually compute their gradients and communicate them. By reading these runtime speeds, DynamicSSP dynamically selects the optimal staleness threshold from a given range on the fly. It actually adapts to the local environment, which reduces the waiting time of your fastest worker without letting those staled gradients spiral totally out of control. But guess what? We can do even better, especially for large neural networks with fully connected layers that are highly sensitive to staled gradients. Let me introduce the ultimate algorithmic breakthrough of this explainer. And this brilliantly illustrates the Elastic Bulk Synchronous Parallel or ElasticBSP solution. Instead of relying on strict, fixed supersteps, this algorithm uses a sequential online prediction phase. It starts with a monitoring phase to actually learn the worker's iteration intervals in real time, and then moves into a prediction phase with a clever look-ahead mechanism to determine the absolute optimal time to impose a synchronization barrier. Let's walk through the specific algorithm that drives this, known as Zipline, step by step, just like a true masterclass. Step 1. Zipline monitors the most recent iteration intervals of each worker, noting exactly when their push requests arrive at the server. Step 2. It uses that look-ahead mechanism to predict a specific number of future iteration intervals for each individual worker. And then, Step 3, the algorithm performs a highly efficient one-pass scan across this predicted timeline. It's basically calculating the precise chronological moment where dropping a synchronization barrier will result in the absolute minimum overall waiting time for all workers combined. It's just a beautifully elegant, dynamic calculation that perfectly balances speed and accuracy. So the crucial point here is, how does this actually perform in practice? Well, the empirical data is phenomenal. When tested on large datasets, ElasticBSP converges 1.77 times faster than vanilla BSP, simply because it's actively minimizing all that idle time. But amazingly, and this is the best part, it also achieves 12.6% higher overall accuracy than BSP. You might be wondering, why? Well, because the highly controlled short bursts of staled gradients that are allowed during the ElasticBSP supersteps actually introduce a tiny, tiny amount of noise. And remember what we said earlier? That noise acts as a regularizer. It prevents the model from overfitting and successfully helps it skip right over poor local optima and saddle points. It literally takes a mathematical flaw and turns it into a training advantage. Incredible, right? Let's move to the final chapter of our syllabus and take a look at where this brilliant synchronization technology takes us next. The elasticity of this algorithm opens up massive, massive possibilities for things like federated learning and edge computing. Imagine trying to train a model across thousands of edge devices, like mobile phones. In those types of environments, worker computational capacities vary wildly and unpredictably due to battery throttling or just random network glitches. Rigid synchronization, it would instantly fail there. But ElasticBSP's ability to dynamically predict and adapt its barriers makes it perfectly suited to handle this wild heterogeneity. It allows us to leverage edge devices for low latency and enhanced data privacy, all without destroying our training times. So I want to leave you with a provocative thought for your final exam question as we wrap up today's lecture. As our neural networks continue to grow exponentially in size and complexity, relying solely on centralized server farms might eventually hit a hard ceiling. Are dynamic algorithms like ElasticBSP the ultimate key to keeping pace? Or is adapting these elastic methods from massive decentralized edge computing the true next frontier for artificial intelligence? Thank you so much for joining me for this explainer. I really hope you found the underlying mathematics as fascinating as I do.